Welcome back to Real Analysis. If you recall from last time, we were developing some of the notions involved in the topology of the real line. In particular, we defined open and closed sets, and we want to talk a bit about the relationship today. So let's just recall what it means for a set to be open. So a set E in a metric space X is open. What does that mean? It's open if what's true? If every point is good. If every point is an interior point. Okay, so that's a rather curious definition. So an example here might be you might have a set here in the plane. And to be an interior point means what? What does it mean for a point to be interior? Yes, Dylan? Yeah, so it's an interior point if every point has a neighborhood around it that's completely contained in this set. So if this is the set E, here's a neighborhood that's completely contained in E. This point also has a neighborhood. I mean, they have many neighborhoods, but in particular, here's one. But of course, the closer and closer you get to the boundary, in some sense here, the smaller the neighborhoods have to be to lie completely within E. But it is still true that that all the points in E have a neighborhood around it that's still within E. Okay? Everybody happy with this definition? This would not be true of a set like this picture, perhaps. Maybe you have a set like this, where this point actually is also in E, but it does not have a neighborhood around it that lies completely within E. Every neighborhood actually has some points outside of E. So this set would not be open. Are you with me? Okay. Now, why do we care so much about open sets? Why do you think we care so much about open sets? We didn't really allude to this last time as we were just making definitions. But why do you think we care about open sets? Let's see. So, of course, you're used to thinking of pictures here in Euclidean space. But I want us to think maybe a little more broadly. This could be any metric space. And really what I'm saying when I say a set is open is I'm saying that if I take any point P, I can push it around a little bit. And it still remains within the set, E. Are you with me? So to be open means I can perturb points in E and still have them stay within E. Okay? So an example might be, let's look at the set of all triples of points in the plane. Take 3 points in the plane. Are they collinear? Well, they are if they're collinear if they all lie along a line. Yes? Okay, but suppose I look at the set of all triples of points that are not collinear. Would you agree that is a collection of 3 points, right? Go ahead and make them ordered if you wish. Ordered points in the plane. That's described by 6 coordinates, isn't it, right? 2 for the first point, 2 for the second point, 2 for the third point. Okay, here's a question for you. Is that set, the set of all non-collinear triples, an open set? Intuitively, yes, right? Because if 3 points are not collinear, if you perturb it a little bit, is it still not collinear? Sure, right? You might, if you're really close to being collinear, then you'd have to perturb it you might not be able to perturb it much, but you could still perturb it a little bit and still be not collinear, right? So that's the idea that's one of the reasons why the concept of open set is extremely important. It means you can push things around and it still lives in the set. Okay? Is that true of this point here? Push it around? No, it's not. You'll leave the set. Okay, so that's what it means for a set to be open. Good. What does it mean for a set to be closed? So that was one definition from last time. A set, let's give it a different name here. K is closed if what? Yes? Good. If K contains all its limit points. Okay. What's the big deal with a closed set? Oh, by the way, this if is the definition if. It means I'm making a definition. K is closed precisely when K contains all of its limit points. Why do you think it's important? Well, it's important for us to understand when a set is closed. Well, if you have a closed set, what does it mean to contain all its limit points? Yes?
In some sense, it's isolated from the space around it, because other things can't get arbitrarily close to it, because if they could, then it would be a limit point, and then they're already in the set.
Okay. So you're thinking about this in terms of what it's not? That's one way of thinking of approaching this. Before we talk about that, what about just in terms of whatever this set is? What's so important about having a set contain its limit points? Well, it might be the case as we continue in our exploration of metric spaces that I'll have maybe a sequence at some point. We'll talk about sequences. And we'll want to know, does it actually have a limit, right? Okay. And if so, is that limit also in the set? Okay. So an example, of course, here is these are points, but we could also be talking, if you're a physicist or an engineer, you could be talking about functions, right? You have a bunch of functions, and you want to know, does the sequence of functions have a limit, right? It could be some waveform of some signal, right? Does it have a limit? We have to define what it means to be the limit of a sequence, but I claim that's very closely related to the notion of a limit point of a set. Okay, so if K contains all its limit points, that's going to be a very useful thing. Okay? Okay, that's just to give you some motivation for these concepts and why we're studying them so carefully. Okay, so at the very end of last time, I defined the concept of the closure of a set. So this was also a definition, but I'll repeat it here. So the closure of a set is a set together with all of its what? Limit points. So the closure of a set A it's defined to be, okay, the notation is A bar, and it's defined to be the set A together with all its limit points. And this prime notation means the limit points of A. Okay. And that, if you like, it might take a set like this, which is this set, if I call this set A, is this set open? No, not if it contains these boundary points. Is this set closed? Doesn't contain all its limit points. But if I throw in all the limit points, which includes a lot of stuff, but in particular includes these purple points that were not in the original set, it also includes all the interior points here happen to be limit points. Is this set closed? Well, it's the closure. We sure hope that we named it, gave it a good name. So here's a theorem. A closure is, in fact, a closed set. Okay, so why is it a theorem? Well, let's see why. It's perhaps not as obvious as it might first appear. And part of the problem is you want to show that this thing contains all its limit points. The set A bar contains all its limit points. But what is a limit point of A bar? Well, it's, whatever some point is. Let's say, so if I want to show that A bar is a closed set, I want to show that if P is a limit point of A bar, then in fact it is in the closure. Sorry. If I want to show A bar is a closed set, I want to show what? I want to show that A bar contains all of its limit points. So if P is a limit point of A bar, then P is an A bar. Right, that's what I want to show. So here we go. Let me draw a fictitious point P. And if you don't mind, I'm just going to blow this picture up because it might be useful here to just make this thing appear plausibly not true. So does everybody see that A bar is the stuff is A together with the stuff the purple extension here? Okay. And now our question is, if I take a limit point of A bar, is P in fact in A bar? So what does it mean to be a limit point of A bar? So consider a limit point, consider P a limit point of A bar. Okay, help me out here. P is a limit point of A bar, meaning if I take a what? Neighborhood, some neighborhood or any neighborhood? Any neighborhood, it will contain a point of what? A bar. Do you see that? That might not necessarily mean it contains a limit point of A. That's the worry. You with me? But our goal, of course, is to show, so we want to show P is in A bar. Would we agree this is the goal? What does it mean to show that P is in A bar? We can either show that P is in A or P is a limit point of A. With me? Okay, so here's the picture that secretly can't happen. It cannot happen this way. Here's a neighborhood of P that is not a limit point of A, and it's not in A, right? This is, we want to show that, in fact, anytime you take a neighborhood of P, if it's not already in A, then what? It actually contains a point of A. That's the goal. Everybody with me? Okay, so let's just do that. Tell me why, if I take a neighborhood of P, that it must contain a point of A. All I know is that it contains a point of what? Of A bar. So let's start with that. So consider any neighborhood. Consider a neighborhood N of P. Remember our goal. Our goal is to show that this neighborhood contains a point of what? A, if it's not already in A. Okay? Point of P. So assume P is not in A. So assume P is not in A. If it is, we're done. Otherwise, we'll show, well, actually, so consider neighborhood. So our goal is to show that this contains a point of A other than P, right? If P is already in A, then we will have already shown P is in A bar. So assume P is not in A. We'll show P is in, that N contains a point of A. Okay, so let's proceed. What do we know about N? N contains what? N is a neighborhood of P, and P is a limit point of A bar. Therefore, N contains a, Willie? Good. So notice, since P is a limit point of A bar, N contains a point. Let's give it a name. How about Q of A bar? Good. So let's give this a name here. We'll call this point Q, and it's sitting maybe right here. Happy? Okay, great. So we have a point Q of A bar. We're trying to show that this neighborhood N contains a point of A. Do you see how we might do that? Yes. Yes, remind me your name. Lindsay, yes. Good. Ah, interesting. So if Q is already in A, we're done. We've found the point, the desired point. That's what Lindsay's saying. And otherwise, if it's not, if it's more like this picture, what Lindsay is saying is Q, that N contains a what? Yeah, in fact, what she's saying is it contains a smaller neighborhood around Q that contains a point of A. So this is the claim. Why must there be such a neighborhood? Why must there be such a neighborhood? This point, we'll call it Q prime. I mean, all I know, of course, okay, so let's start this argument out, and then we will ask some questions. N contains a point Q of A. So if Q is in A, N contains a point Q of A bar. If Q is in A, we're done. We found the desired point. That was this point that we desired. In fact, if you want, maybe it's, I might give this a name. I'll call it Q bar, a Q prime. Set Q prime equal to Q. Otherwise, if Q is not an A, Lindsay says there must be a neighborhood that does what? Well, Q is a limit point of a Q. If Q is not an A, then Q is an A prime, right? Q is the limit point of A. So if it's a limit point of A, it has a, what can I say? Every neighborhood, could be this one, a really big one, contains a point of A. But which neighborhood do you want to focus on? One contained in N, in order to give us the fact that N contains a Q prime. Good. So again, Q is a limit point of A. So choose, consider a, what do you want to call this new little blue neighborhood? How about, yeah, I guess N prime. Consider N of, consider some N prime, a neighborhood of Q that is contained entirely in such that N prime is contained in N. How do I know such a neighborhood exists? N is open. Ooh, interesting. Interesting. Is N open? It is open, it's true. Neighborhoods happen to be open, but how would we show that? This is an important fact, actually. Well, the definition of N is that it's a ball around a central point P. Now the question is, why is there a tinier ball around any other point inside N? Why is N open? Well, we define neighborhoods as open balls, but open balls around a particular point P, right? So why is it true that around any other point there's an open ball, a tinier open ball? Do you see there is something to show here? Why is this? Okay, so I'm going to come back to this, but let me at least write this, your justification, which is true. Finish this argument and we'll come back to that. Okay, so this rests on the fact that such that n prime is in because, or I'll say can do because neighborhoods are open. Nice. Once you have that, then we found Q prime. So Q prime is in N and the desired point. Once again, we've established that N contains a point of A. So we're done, right? I think this is the end of our argument. Is everybody happy with that? Have we found a point inside N that's in A? Yes. What does that mean? That means that P is in fact if it's not in A, it's a limit point of A. If P is not in A, it's a limit point of A. That's exactly what we wanted to show. Okay, great. Let's justify the fact that, so here's a little lemma that we used without thinking almost. Neighborhoods are open. Why are neighborhoods open? Very interesting question. Let's redraw this picture. You give me a point P and a neighborhood around it. Why is it that I can find around any other point, might as well call it Q, that there's an open ball around it that's completely contained in N? Why? Go ahead. Okay, you want to do this by contradiction? Yeah. Okay, let's try to avoid that, only because I don't think we actually need it, but you certainly could do that. Let me just ask you a question. Being this neighborhood means that there is a radius r that defines it. Would you agree? Good. What can you say about the distance from P to Q? It's less than r. Yes? So, I don't know, let's give it a name. So I don't have to rewrite it again. Let's call this distance, let's call the distance A. So I'm going to define A to be the distance from P to Q, and we'll note that it's less than R. Okay, I just made that a sentence by saying, note, this is less than R. Good. What's the radius you would suggest that would work here? R minus A, is that positive? Yes, because A is less than R, yes? Okay, good. So let's call this radius that you want to suggest, what do you want to call it? It's a radius, so let's label it by R. How about R prime? Let's let R prime be R minus A. And now what's your claim? claim is anything that's distance less than r prime from Q is going to be distance less than r from P. Why is that true? Triangle inequality, yes. So this is really where we're using the metric. It's really important that we're in a metric space, otherwise this notion would not be, this neighborhoods wouldn't necessarily be open. Okay, so here we go. It's important that you have the triangle inequality in order for neighborhoods to be open. So the claim is that the n sub r prime around Q is completely contained in n sub r around P. And you can check this if the distance from, let's give it a name, some point x, from x to Q is less than r prime, then the distance from x to P is, help me use this fact. I'm taking a distance from x to P, and what can I bound it by? Using the triangle inequality. dxq plus dqp. Yes? Happy? But what's this going to be less than? Strictly less than? This is strictly less than r prime. And what's this going to be less than or equal to? Actually, strictly less than. Let's see, P to Q. Yeah, less than r minus. It actually equals a. Thank you. And a is r prime plus a is r. This is by definition r. But the important thing is we had a strict less than here, and this is less than this. And this statement justifies the claim. Okay? Okay, so what's the lesson here? The lesson is that the triangle inequality is really important for this property that you thought was intuitive to be true. All right, so we have a good thing that whenever I take the closure, I get a closed set. Let's prove a couple of other facts. Oh yeah, question, Emil. So the question is, you didn't show that the blue set contains any other points. Sure, that's true. It doesn't have to contain any other points. But in this argument, the fact that it contained other points doesn't come from the definition as much as it comes from the fact that Q is a limit point of A. And so it had to contain another point of A that was not Q. Does that help? Excellent question. Okay. Good. So what else can we show? Well, here's another fact that is useful to know. I claim a set is closed if and only if, shorthand for if and only if, it's equal to its own closure. In other words, adding limit points doesn't change the set, which should be evident, right? So one of these directions is completely trivial, and the other one is almost as trivial. So if E is closed, then in the forward direction, what we have is E prime, the set of limit points is in E. So E union E prime is contained within E. And that just means that E closure is in E. So, but E is clearly in E closure. So, since E is clearly in E closure, E equals E closure. Nice. And then in the reverse direction, Suppose E does equal E closure. Well, then E contains all its limit points. Implies E contains all its limit points. Okay. Everybody happy with this? Each time you learn a new theorem, of course, you should sit back and ask yourself, does it intuitively make sense? And this one probably pretty easily does, right? You close something and it doesn't change, and it must have been closed to begin with. Here's a nice fact about closures. Suppose you have a set E that's contained in a closed set F. Well, then I claim that the closure of E, what do you think I can claim about the closure of E? It's also in F. Then E closure is contained in F. Oh, interesting. What this is saying is, in some sense, we know E closure is a closed set, yes? And any other closed set that contains E must contain the closure. So in some sense, the closure is the smallest closed set that contains E, right? So the moral of the story here is E closure is the smallest closed set containing E. Everybody see why this theorem is saying that? You can't, any other closed set must contain the closure. And the proof is actually pretty straightforward. Can anybody see what the proof is? F is a closed set, so F does what? Contains all its limit points. In particular, it contains the limit points of E. So it contains E closure as well. So P, so here's another way to say it. P, if P is a limit point of E, P a limit point of E, would you agree that means that P is a limit point of F? But F contains all its limit points. So all the limit points of E are in F as well. F contains the limit points of E as well as E. And E. Done. Okay. Okay. Any questions about closures? So this is an important some important facts to note. Okay, let's talk about the relationship between open and closed sets. What is the relationship? We have this rather curious definition for open, curious definition for closed. They don't really seem all that related, and yet I claim there's an intimate relationship between a set that's open sets and closed sets. So what's the relationship? What's the relationship? Let me prove a lemma that will perhaps help us see some things. Okay, well, actually, let me not prove lemma. Let me just state the theorem first that we want to show. So I claim that, in fact, if you have a set that's open, in some metric space, X, E is open, I claim this is true if and only if the complement of E is closed. And I have to say what the complement is. So here, the E complement is the complement of E. And what that means is it's defined to be the set of all points that are not in E. So they're in the metric space X but not in E. So the definition is E complement is basically X minus E, where X is the metric space that you're in. And if you don't like this set minus notation, which we defined a while ago, it's basically the set of all points in X such that P is not in E. So what we're saying in this picture is, if you look at everything outside the set E, that's a closed set. Would you believe that from this picture? Yeah, it sort of contains its boundary in some sense. Here, if you look at the set outside the square, it's in fact open. Another way to think about that is it true that if I'm outside this closed set, if I take a point, I can push it around a little and still be outside that closed set? Yes. So let's see if we can justify this this fact. So why is this theorem true? Okay. Well, let's prove it. Proof is not so bad. Suppose I start with an open set. I claim a set is open. Well, what's the definition of open? It means that any point of, let's call it X in E, is what? Is an interior point. All right, great. But what that means, this is equivalent to, means that for any neighborhood, for any X in E, there exists a neighborhood N such that, neighborhood of X, such that what's true about the neighborhood? It's contained entirely in E. Would you agree that's the same as saying, if this neighborhood's entirely in E, it means that N is disjoint from the complement. So the existing neighborhood of N of X such that N is disjoint from E complement. So I just turned this into a statement about E complement. So here's the picture. Here is an open set, E. Here is a point, X. And the claim is if X has a neighborhood around it that is completely within E, then this neighborhood completely misses E complement, which sits outside. Are you with me? All right, good. Now what? Help me. What's my goal? My goal is to show that E complement contains all its limit points. And I've just picked a point that's not in E complement. For any point not in E complement, it has a neighborhood that completely separates it from E complement. So, could this point be a limit point of E complement? No. Therefore, E complement contains all its limit points. Happy? Okay, so for any X in E, X is not a limit point of C. Is not a limit point of EC, the E complement. Because if it were a limit point of E complement, any neighborhood of X should contain a point of E complement, and this one doesn't. So this is the same as saying E complement contains all its limit points. And notice, of course, I wrote this in a with all the implications bidirectional. You can check that the same proof works backwards. So we have E's open if its complement, if and only if its complement is closed. Yes? All right. So complements of closed sets are open. Complements of open sets are closed. What can we say about unions of open sets? There's a question. I think I'm going to erase this board. What can I say about the union of open sets? Is the union of two open sets open? Really? Why? Paul?
Well, I had a question about this.
Oh, you had a question. Okay.
So if a set E is clopin, is its complement also clopin?
Yes. If the question was if a set is clopin, is its complement also clopin? Yes. So, for instance, you know a clopin set R in R. So if you have a in the metric space R, if you consider all the points, that's clopin. What's its complement? The empty set. Is that clopin? Yes. Excellent. Okay. Do you know any other clopin sets in R? Is that clopin? I don't think that set is a open set. It's closed. It's not open. What's that? Are the rationals an open set? Well, to ask if it's clopin means to ask if it's closed and open. First of all, is the rational set of rationals a closed set? No, why not? Doesn't contain all its limit points, right? You can approach the square root of 2 using rational points, right? Okay. So it's not closed. Are the rationals an open set? If I perturb a rational, will I necessarily remain rational? No. Or, if you like, is around any rational, can I find an open set consisting only of rationals? No. So the rationals are not an open set either. They're neither closed nor open. Which also means, I guess, their complement's neither closed nor open, right? By that theorem. Okay, good. So let's talk about the unions of open sets and closed sets. Is the union of two open sets open? Yes, why? Give me an argument. Jenny? Very good. Every point of a union of two open sets was interior to one of the sets. So it's true then in the union of the two sets that every point is going to be interior to their union, right? Because it has a neighborhood around it completely contained in one of those two sets and therefore contained in both of those sets. Okay, what if I take a union of infinitely many open sets? Is that still open? There's a question. How many people say, yes, it's necessarily open? How many people say, no? Okay, not enough people voting here. Let's see. If I take the union of infinitely many open sets, is it necessarily open? What about closed sets? Is a union of two closed sets closed? Union of two closed sets closed. Yes. Okay. We should be able to come up with an argument for that, but most of you believe it's yes, right? What about the union of infinitely many closed sets? Is that necessarily closed? No. Some of you probably have some examples here. So here's the question about unions and intersections. Let's look at some examples here. Maybe this would be illuminating. Suppose I look at the following sets. Ki, which would be the closed intervals minus, let's say, 1 over I. I don't know why I chose the letter I, but okay. It's just harder to write. Minus 1 over I to 1 over I. That's a closed interval. Like so, yes? Centered around 0. So 1/2 to minus 1/2. This would be K2, yes? Happy with that? K3 would be, oh, I don't know if I like this one. Yeah, so let me do this. Let's go from minus 1 plus 1 over 2I to 1 minus 1 over I. That's the example I wanted. So this is still K2, but K3 goes from 2/3 to 1/3. Minus 2/3 to positive 2/3. That's K2. This is K3. K4 is a little bigger. K5 is a little bigger. Get the picture? It's 1/5 away from 1 and minus 1. Now, suppose I take the union of all the ki's. I goes from 1 to infinity. This notation means union all the things for all the k's. What do you get? What set is this if I union all these closed sets? Basically, I get anything from 1 to minus 1 except 1 and minus 1. Are they ever in any of these sets? No. So in fact, here you get minus 1 to 1, a set that happens to be not closed. So here we have the infinite union of a bunch of closed sets that is not closed. So this perhaps points out that we should be a little careful, okay, with applying arbitrary unions. Okay, well let's see if we can prove some things. So let me prove a little lemma. So suppose I have a bunch of, here's a collection of sets. I'll call it E. Why did what am I indicating when I subscript it with alpha? There might be uncountably many in our collection. And if you want, you could also just tell people that you're taking from some index set A if you want, but you don't have to. This is enough to signify we're taking a possibly uncountable collection. I claim the following is true. This fact will be useful. If you take the union of a bunch of sets, possibly uncountable collection, and I take its complement, I claim this is related to the complements of each of the sets in some way. Do you know how it's related? It's the intersection of all the complements, yes. So if you like, really, what we're saying is the complement of a union is the intersection of the complements. Very important fact. Let's prove this. This is not too hard to see why it's true. So let's just, to show that these two sets are the same, you just have to show that if x is in one side, then x is in the other side and vice versa. Yes? Good. So suppose I take a point on the left-hand side. LHS here will signify left-hand side. I claim x is in the left-hand side. This is true if and only if. What does it mean to be in the complement of a union? It means that it's not in the union. Would you agree? And if it's not in the union, that means it's not what? It's not in any of the E sub alpha. So x is not in any E sub alpha. With me? Okay. But if x is not in any of the E sub alpha, then x is in all of the complements. In all the complements. In each one. for all alpha in A. But if X is in all the complements, then X is in what? The intersection. That's what it means to be in the intersection. And all these implications are bidirectional, so you can go backwards this way as well. Happy? All right. So this fact will be very, very useful to us now that we have noted that open sets are complements of closed sets. So, is it true that the union of open sets is open for arbitrarily many open sets? Yes? A is an index set, if you like. It's like normally when you're used to thinking of index sets that are natural numbers, right? So each of you has a bank account, right? And I label the bank account by that's the first one, that's the second one, that's the third one, that's the fourth one, etc. So the index set is 1, 2, 3, 4, ... Here we're going to label every set by some huge index set that may not be countable. It could be 1 for every real number, right? Every real number has a bank account, and I'm going to label it by the real number that it's associated with, something like that. Okay? Okay, but for the most part, you don't have to worry too much about it. We just think of this as any possible collection, and that alpha is just reminding me it doesn't have to be countable. Okay, so here's a theorem. It's a 4-part theorem. So the claim is that the arbitrary union of open sets, what do you think? Is it open or not necessarily open? How many people say the arbitrary union of open sets is necessarily open? That's right. It is in fact open. And similarly, so there's several parts to this. I claim the arbitrary intersection of closed sets is closed. Now, what if you take a finite intersection of an arbitrary intersection of open sets? Is the arbitrary intersection of open sets open? How many people say yes? How many people say no? Can you give me an example? Arbitrary intersection of open sets that's not open? Yes.
Set of open sets that are all completely disjoint from each other except for a single point that they all share. Their intersection will be just that single point and a single point.
Can you give me a specific example? Okay, but are those circles open? Yeah, so I don't think it's possible for two open sets to overlap in exactly one point. But maybe, yes, Emil? Oh, okay. So 0 to 1 over n? Now, if you take 0 to 1 over n and you intersect all those, what's the intersection of 0 to 1 over n? It's empty, isn't it? Right, which is still open. But now you're saying, how about what? Minus 1 over n to 1 over n? So here's an aside. Check this out. If I take the intersection of minus 1 over n to 1 over n goes from 1 to infinity, the claim is that this is what's inside every set from minus 1 over n to 1 over n. The only point in all these sets is what? 0. Is this an open set? No, it's not open. But each of these is open. So the arbitrary intersections of open sets not open, but if you only take finite unions, finite intersections of open sets of open sets is open. And the corresponding fact is that the finite union of closed sets is closed. Okay, very, very important facts about open and closed sets. So let's see if we can't give some justification for this. So you're going to help me do this proof. Let's do part A. Now, Jenny just gave us an argument for why the union of two open sets is open. How would you show the union of arbitrary and many open sets is open? Well, very similar way, right? So let's take a point that's in an open set, a union of arbitrary union. So let's let, if X is in, let's say A sub alpha, union over alpha. Oh, sorry, I don't want to use the same letter as this A. Give me another letter you like. How about C? Oh, it's a U. U is often used for open sets, by the way. It's customary to use U for open sets. Oh, that kind of looks like the union symbol, though, doesn't it? I'll be very careful. I'll give every U a tail. Is that okay? How's that? Okay, here we go. Suppose these are open. So I'm just going to say that each of these is open. And it's a union. What does it mean to be in the union? Well, that means that the point is in one of these sets, right? Now, what our goal here is to show that every point in X in this union has a neighborhood around it that's completely contained inside this big thing. And the strategy is, oh, well, this means it's in one of the things, and that has what? A neighborhood that contains this and is completely inside. So that's the goal here. So we're just going to say this then. This means that X is in some U sub alpha, and which is open. So that has an interior. It has a neighborhood around it because it's an interior point, which is an open set. So X has a neighborhood. Let's call it N. That completely N sub X, such that X is in N sub X, which is completely contained in U sub alpha. But now what? U sub alpha is inside what? The union. As desired. What did I find? I found a neighborhood, which gives, so if you want to help the reader, you might say, so we found, so we have the desired neighborhood. Everybody happy with that? Yes, question. Yes, excellent point. So the question was, should I have used a different subscript besides alpha? Because alpha here was general, and you want to pass to something specific? That's the question, right? Yeah, and the answer is, you could do that. It clutters things up a bit, so people traditionally don't, if it's clear. But if you want to make it very, very clear, you might pick a specific alpha, and you wouldn't call it I because that makes you think of a countable index. So what you do is you take alpha and you might give it make it look different from the generic alpha. Some people might put a naught, which is also troublesome, or you might put a hat, It just clutters things up a bit. So that's different than this alpha. Yeah, I see. That is something to worry about. If you like, or you might even just call this U sub beta. But then you'd have to indicate that beta is in A. Yeah.
But if you just like put a hat for some U alpha.
Yeah, that would be clear if you did that. Okay, good. How do you prove part B? Help me out here. Let's see. Arbitrary intersection of closed sets is closed. Okay, good. So let's put the ingredients together. You could certainly do this directly from the definitions, but we've already done some work. Look, suppose you have, let's say that you have a bunch of sets, let's call it B sub alpha, and they're all closed. What's true about the complements of the B sub alphas? Then the complements are open. Let's call those U sub alpha. Why not? Then the U sub alpha, which are the B sub alpha complements, are open. Yes? Excellent. Okay, help. Use what? Use this lemma, which would apply to what? Yeah, so these are a bunch of things that are open, and the union of a bunch of open sets is automatically open. So its complement is closed, but isn't B U sub alpha complement just B sub alpha? So use the lemma noting that U sub alpha complement is closed. Is B alpha. So that's the right-hand side, and the left-hand side is basically the complement of an arbitrary union. Then the left-hand side of the lemma is the complement of an arbitrary union. And the right-hand side is what? It is the intersection, arbitrary intersection of closed sets. So I'm not going to fit this all in. Arbitrary intersection of closed sets. Sorry. I'm sure the video is not even capturing this. Okay, but that's the idea. So I'm going to call this proof sketch, because I obviously didn't write things out carefully. Now, I claim C and D are very similar. So I'm going to let you, well, they're not similar. D follows from C in a similar way that B follows from A. To establish C, you have to do something slightly different. So let's just do that. We'll do C, and then we'll leave D for someone else to do. Okay. Finite intersections of open sets are open. This one's a little more interesting. Here's a couple of open sets that perhaps there's one open set. Here's another open set. And I'll call this one U sub 1 and U sub 2. Why is their intersection going to be open? Why is it that if you have an interior point, if you pick a point in the intersection, then it's interior? Why is it if I pick a point in here that it's going to be interior to their intersection? Now, what do you know? You know this point is interior to what? U1 and U2. So why is it interior to both of them? Good. Here's one that's completely contained in U1.
Find another one completely contained in.
Here's another one completely contained in U2. Take the smaller one. Good. And if there were finitely many, you would do what? Take the minimum radius one, right? Now, why would this idea not work for infinitely many intersections? I mean, clearly it can't because we see a counterexample. But what would go wrong with this idea for infinitely many? The minimum doesn't necessarily exist, right? Because these concentric circles could get what? Smaller and smaller and smaller and smaller. So it doesn't have a minimum. It has an infimum, but it's not going to be greater than 0. That's the problem, right? Okay, great. So this is the sketch here is there exists a neighborhood R sub I of X for each A sub I. Oh, sorry. What do we call it? U sub I. So take let's let R be the minimum of the R1 through R sub n. And then the claim, this is the claim, is that n sub R sub x is shows x is interior to the intersection of the U sub i's. I goes from 1 to n. And this is a sketch, so I haven't done the work, but I've just indicated how it goes. Okay, that's the main obstacle. All right. Any other questions about D follows for similarly by taking complements? Any other questions about the relationship between open and closed sets? Jenny? That's correct.
If you were to say somehow define the is there some difference between maybe using countably many versus uncountably many or something like that?
Okay, so the question for the people listening on the video was, is there some distinction? This theorem indicates a distinction between finite and arbitrary. Is there some finer level of distinction that involves countably many unions and uncountably many unions? And the answer is no, not as pertains to unions and intersections. Yeah, there are distinctions between countable and uncountable unions of countable and uncountable collections of things when we start talking about some other topological concepts. Other questions? Okay, good. So let me just indicate, I'll maybe put a couple of more definitions up that we probably should at least mention. And then call it a day. So here's a definition that we should probably say. I think I might have said this last time, but not written it down carefully. So what does it mean for one set to be dense in a metric space X in a metric space X? Well, it means that there are a few ways to say it. I'll just mention what the book says, and then I'll give you another definition that's equivalent and easier. So the book's definition is a set is dense if every point of X is a limit point of E or in E. Okay, so an example of this would be, save a little room because I'm going to give you an alternate definition. Q is dense in R. Because isn't it true that every point of every real number is a limit point of rationals or a rational? Yes. Okay. That is true. But here's another definition. So another way to say this is what? Well, if every point of x is a limit point of E or in E, what's it mean to be in E or a limit point of E? In the closure. So another way to say it is, you could say, if E closure is x. Would you agree with that? That's equivalent. Yes? Or, so I'll make this a biconditional because you can show that. There's another way of saying what it means to be dense. If E closure is x, that means that any open set, I claim, any open set in X contains a point of E. That's what it means to be X to be a limit point. You give me any point in X and then any open set around it, I claim will contain a point of E. That's what this means, right? So might as well just say take any open set. So every open set of X contains a point of E. And this is probably an easier way to think about what it means for one set to be dense in space X. Okay. So just to give you some intuition for where this goes with other metric spaces, you might want to know, for instance, if I have a bunch of functions, if you're an engineer, you'd be worried about this. You have a bunch of functions. You want to know, can I approximate it by sines and cosines, or sums of sines and cosines? That's what one Fourier analysis is all about. Oh, well, that's in some sense saying, is a certain subset of functions dense in a whole space of functions, right? Are the polynomials dense in the set of all continuous functions? There's a question. Are the set of linear combinations of sines and cosines dense in a set of periodic functions? Okay? It's really what we're saying. Okay. That is probably a good place to stop. Next time we're going to begin one of the huge concepts in this course, and that's a concept of compactness. What does it mean for a set to be compact? Okay?